Okay, so today I want to talk about two things. The first is I want to look at the reason why we have been working on these type classes and just talk a little bit about um, parametricity in general, and I'll define that in a second. And then I want to look at the traverse type class, which is one of the most useful and, practically speaking, one of the most common things you're going to run into when working with Scala. Okay, so let's talk about parametricity. So that's a big word. And what I mean when I say parametricity is that we want to make parameters out of everything in a given function definition such that what's left are only the absolutely essential parts to the function we're writing. So for example, let's start with something very easy. Let's say we have a function here. We're going to call it foo. We'll define it as taking a single value of type A and returning an A. And the question that I will, will ask is, how can foo, or if someone gives you this type signature in Scala, what does foo do? What's the implementation of this method without looking at, the code, without being given documentation like Scala doc? Can you figure out what this particular method does? And in this case, the only implementation of this that's possible in Scala is to return A. At least if we limit ourselves to a safe subset of the Scala language. Because, for example, like we can't even use null here. We could certainly throw exceptions. So we're going to remove exceptions from our safe subset. So for example, we could say throw new we could implement foo this way, but we're going to remove that from our subset of the Scala language and just work with pure values. And we're only going to work with things that, or methods that, or features, I'll say, of our types that are expressed in the type signature. And in this case, we have this generic parameter A, and we see nothing about it. So specifically, we're going to restrict ourselves from not using toString equals or hash code. Even though theoretically, we're running on the JVM and everything, is an object, and we have equals toString and hash code on everything. If we remove that from our subset of the language, then the only possible implementation of this method foo is the identity function. So let's do another quick example. Let's have a different foo. And the question, in this case, we're going to take two values, both of type A. We're going to return an A. And the question is, what is, how could this possibly be implemented, given the restrictions we just gave? Does anybody want to jump in and describe how this could be implemented? There are two possible definitions.
You either return A or X or you return Y.
Right. Those are the only two definitions that that we could possibly write, given our restrictions of only relying on things that are in the types. Now notice if we allowed ourselves to use hash code, we could do different things. We could say if X's hash code, for instance, is greater than Y's hash code, then return X, otherwise return Y. It's some kind of weird, ordering based off of identity system hash code stuff. I mean, strange stuff, right? But theoretically, we could do these things if we allowed ourselves access to methods from the JVM. But again, we're only going to allow methods that exist in the type signature here. All right, so let's do a slightly more complicated example. Oops. All right, so anyone want to jump in? What's the implementation of this function?
X.
X, right? And let's do a slightly different version. We're going to change the return type to string. Now what's the implementation of this?
Y.
Thank you, Matt. And by restricting ourselves from using hashcode toString and equals, these literally are the only implementations of these functions. So specifically, it is not legal to write this. Right? Like, the type here is the same. We're saying x plus y. Well, x, all we know about x is that it's some type A. We know nothing about A. So, of course, what's happening here is like some any2 add string implicit is kicking in and adding the plus method, which takes the toString of x and then concatenates a string to it. This is probably one of the most confusing features of Scala, is this implicit conversion here. But again, we're not allowed to use toString, so this is not a legal implementation of foo if we remove toString from our language. Okay. So let's do an example that's a little more interesting. Again, we're going to take an A. So the question is, what are the legal implementations of this method? So given a list of A's, we're going to return a list of A's. We could certainly just return as. That's certainly one implementation, right? So foo would just be the identity function. We could return various subsets of our input list. So for instance, well, that's not going to work. Let's say, I don't know. Well, could we do something like if this is empty, then we'll return nil, and otherwise we will return oops, sorry. Sorry. We'll take the tails, convert it to a list, and take the head. There we go. So this would be a possible implementation of this. And the idea here is that, like, while we made our type a little more complicated in that we took a list of A's, still the list of possible implementations of this function is still fairly small. We can't do anything with the specific A's, like the specific values in the list. So for example, we couldn't return a list that's in a different order because we don't have an ordering for A, right? We've got no way to sort by the values. We can take this tails issue here is that we took various like subsequences of the list and returned it, but they're all just a very small set of possible list results. Let's do one other example. So we're going to take our same input list of A, but we're going to return a list of B. In this particular case, all we did was add one additional parameter. So we went from like lots of possible methods of foo when we were returning a list of A, although still, compared to the grand scheme of method implementations, it was still a pretty small list. And now we just changed the output type here to be list of B, and the question is how many implementations do we have of this method? And it turns out there's only one. What's the one and only implementation of this method?
Nil.
That's right. Yeah. Right, and you might think like, well, okay, if I have a list of A, I can convert it to a list of B if I can just convert an A to a B. But we don't know anything about either type A or type B, so there's no possible function we could write that can convert an A to a B. And this works just as well for any fixed type too. We don't even need B to be like a parametric type. So for instance, we could say, we're going to return you a list of string. And again, the only possible implementation is nil because we know no information about how to convert an A to a string. Let's do another one. This has quite a number of implementations. In fact, I can tell you the exact number. It's 2 to the 32 minus 1. And the reason it's that is that the only possible implementation of this is to return a specific integer that ignores, that we're going to ignore the input element. So we can make this equal 0, we can make this equal 1, we can make this equal 2, but there's absolutely nothing we can do with this parameter a. Right, so in all these cases, we're seeing like this theme that because we introduced a parameter, in this case a type parameter, we applied information hiding to the implementation of this function. We hid any information we knew about this type A from this implementation, and hence we're guaranteed that this implementation doesn't use that data. By doing so, we can really limit the set of possible implementations down to something that's very, very, very precise. And we're going to see this pattern show up a lot as we continue to use these type classes, where by applying this notion of parametricity to the definition of our methods, we've extracted out just the exact requirements we have on the data structures in order to express any given algorithm. And by doing so, the implementation of that algorithm a lot of the times falls out or comes for free because it's the only possible way to combine, the input parameters to create the output type, a value of the output type. So this whole notion of parametricity, I think, is really interesting because often, at least like from OO or from like the Java environment, we tend to think of defining methods, classes with generic parameters as an effort in abstraction or as an effort in generalization. And in fact, you might hear people say like, well, you're never going to need that, right? Like we have the you aren't going to need it principle. So let's not overgeneralize a data type to be parameterized by all these types. If you need a specific method that works on like a map from int to your data structure, just write that method directly. And I think the interesting thing here is that the notion that introducing parameters is overgeneralizing is actually false. What parametricity shows us is that you're exposing too much information to the body of that particular class, method, trait, whatever it is that you're working on. And by doing so, you open up so many possible implementations that it becomes impossible to reason about the code algebraically. And so actually by introducing parameters, introducing parametric definitions of our functions, it's we're not enabling code reuse. That's a nice side effect that we get by doing it. But rather we are limiting the amount of data we need to keep in our head in order to work on this particular part of the system. So it's really more about modularization and correctness than it is about generalizing for code reuse. Okay, and we'll come back to this notion of parametricity. If you want to get practice with these, there's a nice Twitter account. It's actually called Parametricity. I'm going to try to pull it up here. Oops. So here is an account that gives little examples. Now they happen to use Haskell syntax, but they give little examples and then tell you exactly what, or various facts that you absolutely know about this particular code based on this notion of parametricity. So anyway, if you're interested or want to kind of have some brain teasers, it's fun to go through these and see what you can come up with. Okay, so last time we talked about the foldable type class. And remember, foldable was, at least in structures, we defined fold left and fold right as our abstract operations. And these looked very similar to the fold left and fold right methods that we have on just normal collections. Right, so here was like our type constructor wrapped value, like an f of a. And when we fold left across it, we'll start with an initial value. And we'll take a function of the accumulated b and the current value a, returning a new b, and we can fold all of those into just a single b. So we saw fold left and fold right would be our two abstract operations. Then we saw fold map was a way of iterating through each individual entry, each individual a value, applying a function to convert it to a b value, and then using the monoid to, for value of type b, to combine them all together into a single result. We did some examples with fold map of, counting the number of elements in a list, things like that. We also saw fold, which was just fold mapping with the identity function. In that case, we're going to require a monoid for the a type. So when we do a fold map, we're just going to return a type a, and we'll just end up using the combine method on the monoid of a to combine all the values into a single value. Now, I said this last week, but it's worth repeating that foldable is a lawless type class. You can see structures doesn't actually define laws at all for foldable. It turns out you can define some consistency laws, but they're not laws in the same sense of things like the functor laws, the monad laws, the applicative laws. What I mean by consistency laws is that we want fold left, fold right, and fold map to all produce the same value if you call them with the similar functions or functions that algebraically can be refactored into each other, or factored into each other. We want to be able to get the same results back. So it's not okay if someone tries to implement the foldable type class and implements fold left to do something completely different than fold right. Right? We want fold left and fold right to kind of be mirrors of each other, just like in a typical collection, it's just changing the starting point per se. And similarly, we want fold map to have a certain behavior as it relates to the way fold left and fold right works. But that's different, right? That's different than the functor laws, because when you think about it, the functor laws were about how does map behave, right? With functor, our only abstract operation was map. And when we look at the functor laws, all of the abstract operations, all of the laws themselves constrain the possible implementations of map. And this is really important because when you go to implement a functor for a given data type, you by definition are losing parametricity, right? Like here, our definition of map, is abstract, and our definition of, let's say, lift is very parametric. Right? Like lift takes a function from a to b, and the only data that it has about, in order to implement this, is that it knows it's got some function a to b, and it knows it's got a map method that adheres to the laws. And hence, the only implementation that lift could possibly be is the one we wrote down. So when we're working in the functor type class itself, defining the lift operation or defining the void operation, everything's very parametric. When we go to implement map directly on functor of list, we have a lot more information. We know now that our type constructor type is list, right? So we're less parametric. And hence, our laws are designed such that we don't take advantage of the information about list in such a way that would break the reasoning of these other derived methods. So, how can we do the same thing with foldable? What could we say about the behavior of fold left such that we constrain the implementation of fold left in a more meaningful way than just saying fold left is fold right in reverse? And it turns out we really don't have anything to say here. There are no real good laws for the foldable type class short of consistency laws, because I mentioned this last time too, at the end of the day, everything we do with foldable could be implemented by defining this. As our one abstract operation. Right? So if we defined this method toStream, given an f of a, and I'm sorry, that's what it should be. Given an f of a, convert it to a stream of a, then we can define all of the rest of these, including left and fold left and fold right, as derivatives of toStream. And so, there's just nothing to say about the way toStream gets implemented. It's completely arbitrary. So the foldable type class exists solely to provide access to these operations. It ends up just being really useful from a code reuse perspective, even though it doesn't really give us anything we can reason about. Well, so if we add some more constraints to the foldable type class, we get something we can reason about. And that would be the traversable type class. Now, traverse or traversable, traversable is taken by the name traversable is taken by the Scala standard collections library, right? So we've got like scala.collection.traversable. So as a result, we can't use that name without causing import conflicts for folks. So we're just going to call it traverse. And here's what we're going to do. We're going to start with the definition of functor. So a traversable type class, or the traversable type class, is going to be a constrained version of a functor, something that has that map operation, that also has the folding characteristics we saw. We can fold left, we can fold right, we can fold map. And it's going to add one abstract operation, which we can reason about. And like if you kind of squint your eyes a bit at this definition, it sort of looks like Flatmap. Kind of. Let's just look at the values for a second, and we'll come back and look at the types. We take a value of f of a, and then we take a function from a to g of b. And we're going to return a g of f of b. So let's compare that for a minute with Flatmap. Now, Flatmap doesn't exist in the traverse type class, and it doesn't exist in any of our parent classes, right? We got Flatmap from Monad. But let's just pretend it did for a minute and just compare the type signatures. We're going to line them all up. So with Flatmap, we took an f of a, and we took a function from a to f of b, and we returned an f of b. Right, this was our main, short of pure, it was our main definition of a monad. So traverse we're going to do a little bit differently. It's going to be an f of a and a function from a to g of b, a different type constructor. And then we're going to get back a g of f of b. So this is sort of the inverse. Right, like if each individual value that we're applying the function to results in a g of b, we're somehow going to distribute the f over the g, if that makes sense, and get back a g of f instead of an f of g, for instance. And don't worry, we'll look at a lot of examples on how to do that. Now we're going to require one constraint on our type constructor here, g. And that's that it needs to be an applicative type constructor, where we need an instance of the applicative type class for g in order to be able to call this traverse function.
Can you talk about this difference between sequence and sequence U? I mean, this is more from Scala Z land, but...
Yeah, I will. Let's look at sequence, and then we'll jump to the REPL and do a lot of examples of this stuff. So sequence is a little bit different. Rather than starting with just an f of a, like we did with traverse, with sequence, we're going to start with an f of g of a. And we're not going to take any other parameters. You call sequence with an f of g of a, we'll give you back a g of f of a. So we're just going to swap f and g, is all that sequence does. The implementation of sequence is very interesting, I think. We start with f of g of a, passing it to traverse. right? So these, like the namespaces here, are separate. We've seen this before as we've done other examples, right? Where like the a in this function is not the same a as that's up in this function. So when we plug these types in, if we traverse an FGA, then the a up here, this a up here, ends up being our g of a down here. And now when we call the function traverse, we just need to take whatever our a type is and return a g of b for some type constructor g. Well, we have, our a up here, right, is this g of a down here, and g of a is certainly a type constructor. So we can just use the identity function. That's what we do right here. When we traverse, we just traverse with the identity function, which says just return directly our g of a. And because we have this applicative definition for our g type, we're allowed to call traverse then. So let's see an example of this type class. So we'll just do a very simple example that happens a lot. We have a list of options. So let's say we have a list that has so we have a list of option int, and we have 3 sums. With sequence, we can just switch the list and the option, so now we have an option list of int. And you can see like the kind of expected thing happened. We distributed the list over the sums, right? So we got a sum of a list 1, 2, 3. If we have like a none inside of here, let's just put a none in the middle here, and then we sequence, we get a none back. So the appearance of any none in our list is going to result in a none, at least when using options. Whereas if we have all sums, we get back a regular list. Let's do a simple example of traversing. So we have this list 1, 2, 3, 4, 5. We can traverse this list, and now we just get an individual number, the function here. We'll have a function from integer, a number n, and we need to return a type constructor. And we can return any type constructor that has an applicative instance, but we're going to go with option for now. So let's just say option n. So all we did here was lift it into the option constructor. And you can see the net result is we end up with an option on the outside and the list 1, 2, 3, 4, 5 on the inside. This certainly wasn't the most efficient way to wrap a list of numbers into an option. But imagine that each individual step here, each operation here, was doing some validation perhaps on this number. And then if any of them returned none, we would have gotten a none back for this overall list. So of course, an example of that would be like, if n is greater than 3, return none, otherwise return some n. And we'll get back a none overall for this particular list. So I said, the traverse class is one of the things you're going to use the most because it comes up all the time when working with like collections, when working with futures, when working with ethers. It's very common, for example, to have a list of futures, but you want to get back a future of a list of the results. It's so common, that's so common working with futures that it exists directly on the future class in Scala. You can see here we're on Scala concurrent future, and I'm on the companion object. And you can see the definition of traverse and sequence directly on future. And in a lot of ways, I think the existence of traverse and sequence on the future class is an indictment of the Scala standard library approach to reusability. What we saw in our definition of traverse and sequence is that it's just a functor that has this traverse operation. Yet if you look at the definition of traverse and sequence on future, you can see, one, it's defined specifically for futures, not for like any type class that supports this traversable notion. So for example, there is no traverse or sequence on list in Scala, right? This is hard-coded specifically to futures in Scala. So that's the first sort of axis or the first example of these two methods violating like the don't repeat yourself principle, or really violating parametricity, is that they are specific to a given data type rather than being generic for anything that has a traverse operation. But the other thing that they do, the other big violation of these two methods, is that they only work on, look here, a list, or like an M of future A, where M is a subtype of traversable once. So this is really interesting. Like in our case, our sequence and traverse worked with any applicative, right? Our type constructor, the inner type constructor, could be any applicative. And here, it has to be a future. And the outer type was worked with any traversable, and here it has to be a specific Scala collection. It has to be a collection that extends from traversable ones. So our definition of traverse is much more general than the standard library definition when working with futures. But you know, if you've ever worked with futures and you had a list of futures, I'm sure you've run into this case where you want to combine all of their results and get back a future of list. And this is exactly how you would do it.
Is the traversable once because futures aren't, of course I can't remember the name of it. Is there a reason it has to be traversable once?
Versus like what else?
Just traversable?
Oh, traversable once is just more general. Like traversable is stronger in what it takes to implement. I think traversable once is almost the most general type in the Scala collection library. I say almost because let's look at it. It has one parent class, gen traversable once. And this type, gen traversable once, is the most general type in Scala collections. The only difference between these two is that gen traversable once might be a parallel collection. Traversable once will not be a parallel collection. But like, why is future defined to take a traversable once and not a gen traversable once? You know, I don't know. I mean, I do know it's that the Scala collections library is just much too large, and the types that it describes in the type hierarchy are all about finding a balance with code reuse, as opposed to finding like things that actually have meaningful abstractions like these type classes that we're working with. But anyway, that's a bit of a opinion, I suppose. So like, I mean, so sequence I think is at least easy to see in a lot of cases, in that, you know, if you have an f of g and you need a g of f, then you can just call sequence, hope that you've got a traverse implementation for f and a applicative implementation for g, and as long as you do, everything just works. I think traverse takes longer to get used to. So I want to use an example with futures, although I don't have, right now I don't have an applicative instance for futures, so this isn't going to work. But like, let's say you had a collection like messages, and this was like a list of, you know, whatever, foo and bar and baz, whoops. And now what you wanted to do was like send each of those messages off to, let's say, actors, and wait for the responses from all of them. So really what you want to do is something like messages.map, and you've got a message here, And then maybe you say like, my actor will ask it for the message, send it the message, map the result to some, whatever response. So now you've got a list of responses, and then you could sequence that list of responses into a single future. Here we really have a list of future responses, right? So we have a list of futures. We can sequence that to get a future list. Well, anytime you see this pattern of map then sequence, that's really just traverse. So instead of mapping and then sequencing, we can just do the whole thing in one step, and we just say .traverse. And the net result here would be our future of list of response. So let's try something. We're going to open a REPL that has Scala Z on the class path, since it has more instances defined than I have in structures right now. And we'll try a couple different examples with Traverse. Okay, so let's just do some of the examples we just did. Like take list 1, 2, and 3, and we can traverse that list. And we'll just wrap everything in an option. And we get back our option list, right, where we distributed the option over the list constructor. Let's try this one. We'll take list 1, 2, 3. And now what we're going to do is say if n is even, we'll return a right. If it's odd, we'll just return a left with the string odd. Oh boy. We're going to want that. We're going to want that. All right. So let's see what error message we get here. So we get this message that says there's no type parameters for method traverse. And you can see, Scala has already kind of stuck some of the type parameters in for us, right? It knows we're trying to traverse a list of int. So it says your traverse method on a list of int is going to take a function from int to g of b for some g. We don't know what g. And we require an applicative instance for g, and we'll give you back a g of list of b. But it's seeing that we're returning a function int to a string or int. And that's what all the rest of this error message is really telling us, or at least this part of it. It basically says this all again. It says it found this function int to string or int, but it requires it to be int to g of b for some g and some b. That's what these little questions are. Like, I don't care what g it is, but there's got to be some g with some b. And this is a problem with Scala C and the Scala language right now, is that higher kinds are sort of like a bolted on feature, like these higher kinded types, in this case type constructor g, and specifically given a value whose proper type is an applied type of a higher kind, and the higher kind does not have the same shape as this, as the target higher kind, there'll never be inference occurring. Or Scala Z can never figure out that these things are compatible shape-wise. And that sort of makes sense here, right? We're saying you got to return a g of b, and yet we're returning like a applied type of a binary type constructor. Right, like this disjunction type takes two values, a left value and a right value. And we saw this like earlier, in previous weeks when we looked at like the map type. When we wrote a functor for map, we didn't write a functor for like map itself. We wrote a functor for map given a fixed k type, and we let the value type vary, right? And that's kind of what we want to happen here. We want to say like, well, no, like our type constructor, our G, is the type, string or question mark. In the same way that we wrote a functor for map, we said our type constructor was map of k comma question mark. And hence, our B is really int. But anyway, Scala will never infer that. It's not capable of inferring that. So Scala Z provides this thing called traverse U, which just works. So traverse is implemented the kind of plain, very simple way, at least from a type perspective, of you tell it exactly what the shape of everything is that you want. You want a function from A to G of B, and you want an applicative for G, and you'll return a G of list of B. But then to work around this limitation in Scala's type system as it relates to higher kinded types that don't come from the same, that don't have the same kind, Scala Z provides this unapply version. So anyway, it's very ad hoc in Scala Z. What I mean by that is that functions that are used a lot tend to have unapply versions if they otherwise wouldn't work. If otherwise inference wouldn't work, then someone has probably gone to the trouble of writing an unapply version of it. So traverse U is certainly one of those things. You can see it as well if you just do this. Oops. Right, so we'll take like a list of disjunctions here, and we can just sequence it, but we get the same error. In this case, it's a little bit different, but you can see it's the same idea. It's saying that it can't find proof that a disjunction of nothing comma int is a G of B. And it all gets back to the same root error of this kind incompatibility. Yet if we just do sequence U, normally that would work, but there's something nasty happening here with the nothing. So to show you what I mean, if we said all right, so if we actually gave it a left type here, we'll say string, then sequence U works fine. So again, like this actual error here, when we first try to use sequence U, ends up being something unrelated as it relates to like contravariant type lookup or whatever, implicit lookup, or maybe not. But anyway, when the left type is known, it actually works fine. Okay, so the key part of the traverse type class, the key abstract method, the only abstract method is traverse itself. And the abstract methods we get from Functor and Foldable as well. And then the key derived method is sequence. Just like Functor, just like applicative, traversable functors can be composed. So if you have a traverse instance for like f and a traverse instance for g, you can create a traverse instance for f of g. So this is a lot harder in a sense to think about, right? Because like the composite functor, for example, is relatively easy to think about compared to this one. Because there you're just saying, like, if I have an f of g of a, I can map an a to b to get an f of g of b. Like, I'm just kind of zooming in, through the f, through the g, down to the individual values. But sequence and traverse are already, defined to take like another type constructor as a parameter. So just on a regular traverse f, we're already dealing with like a g of b and a g of f of b. So if we compose a traverse f and a traverse g, we now have to deal with 3 layers of things. And you can see that in the composite definition here. The composite traverse instance, for an f and for a g, you can see is defined as extending traverse of f of g of x, and it extends the functor composite and the foldable composite. And we get the traverse instance for f and the traverse instance for g. And then all you do is like plug all of those values into our abstract methods, like in the same way that an IDE would just generate this method for you, at least the type signature. Literally the exact same way. Your IDE should be able to do this. You can see you get this definition for traverse. And so you start with an f of g of a, and you have a function from a to h of b, where h is some other type constructor, and now you get back an h of f of g of b. So I mean, it gets pretty hairy to look at, but you can see like the implementation actually sort of just flows in the same way that like the composite definition of map just flowed. Whereas like the composite definition of applicative was pretty tricky, right? I don't know if you remember, but like all the way from our second week, when we tried to write the composite apply, it got really nasty. But the composite definition for traverse ends up just being 2 traverses, in the same way a map was just nested maps. I mentioned once before when we looked at applicatives that there is, applicatives were first sort of documented by Connor McBride and some of his colleagues in a paper called Applicative Programming with Effects. That's where we get the definition of an applicative functor. That same paper defines the traversable type class. And that paper also defines a set of laws for the traverse operation. There's actually a couple different ways to define this. Like in the same way that monad we talked about, there were 2 different ways. I don't know if we talked about this or not, but with applicative, there are 2 different ways to define an applicative, like 2 different things you could make abstract. With foldable, we've already talked about both last week and this week, how there were like 3 different ways. You can make fold left, fold right, or fold map, or 2-stream. Turns out there's a couple different ways to do traverse as well. And in that paper, the laws are presented. Unlike the laws we looked at with like functor, like the functor laws were relatively straightforward. Identity and composition. The applicative laws were certainly less straightforward, but maybe each one of them isn't particularly hard to follow if you just kind of work through them. Well, the traverse laws are much more difficult to follow. So actually, they're not even in structures yet, because structures doesn't have enough power to represent them, at least at this point in time. If you are interested in the traverse laws, I would recommend looking at Scala Z source code, or hopefully one day Cat source code, although Cats doesn't have support for them yet either. Because again, they're a little more involved to write down. So the traverse laws in Scala Z are defined here. And so I don't want to go through these in detail, but like you can see that there are things like there's some identity of the traverse function. There's this thing called sequential fusion. There's something called parallel fusion. And then the one that we don't have the power to talk about right now in structures is this naturality law, because it requires this natural transformation between type constructors. But nonetheless, like these are all documented in the paper. So if you're at all interested, go ahead and take a look at it. But otherwise, you can just try to implement the traverse operation, and if you think you've implemented it successfully, try to just run tests against your traverse implementation using the laws of whatever library you're using. So if you're using structures, eventually structures will have the traverse laws implemented. You can just run your algorithm against it. One other thing I wanted to say today, and that's if we go back to Foldable, you can see Foldable has these 2 derived methods that we didn't talk about, traverse and sequence. But you can see there's an underscore on each, traverse underscore and sequence underscore. And so let's look at this type signature and compare it to the traverse and sequence we just looked at as part of the traversable type class. So actually, let's just steal traverse, for instance, and put it above, and so we can compare. All right, so line 17, I just put a space in so we can align everything, but traverse without an underscore, you can see matches traverse with an underscore all the way up to the return type. So, we have an f of a, and we have a function from a to g of b, and we require an applicative for g, but traverse is actually going to give us a g of f of b, and traverse underscore is just going to throw away the result and just give us a g of unit. Or I shouldn't say throw away the result, but as we convert each a into a g of b, eventually we get a g of unit. And like our type constructors, remember, are modeling effects, right? So like the option type constructor is modeling, the presence of a value or not, whether it's there or not. Our list type constructor is modeling like this uncertainty about all these different values. You've got 5 different values. Maybe your right answer is one of them. Our future type constructor represents a computation that's running that's going to finish later. And so like, what's the point of traversing into a unit? And the idea here is that you don't care about whatever result got built up, but you do care about the effects that occurred along the way. Now, of course, the traverse type class extends from foldable, so we can always use traverse underscore in these examples. Right, like so here was our traverse case, and if we just do traverse underscore, we get back an option unit of a none. If we did that same example with only like lists, or only with numbers up to 3, we get back some unit, right? So in this case, if all we cared about was whether or not any value existed in our foldable, if any of them were a none, we didn't actually care about the overall value. We could have just done traverse underscore and then just done is defined, for instance, on the value. So why does traverse underscore exist as a standalone operation, as opposed to maybe a different implementation? Like you could define traverse underscore if you moved it to the other type class as just traverse of FAF, and then you could map the results of that and just say ignore the results and convert it to unit. And type-wise, that absolutely is fine. It'll compile no problem. But note that our implementation here requires now a full traversable type constructor as our outer f, whereas traverse underscore here was defined on foldable. We don't need something that's completely traversable. If you can't define a traverse method, no problem. You can still use traverse underscore, and we can write a completely different implementation than this implementation here, and still be able to calculate the result. So that's the bulk of the topic I want to cover today. Do some questions real quick. So one question that's outstanding in the chat is, do the traverse laws explain why traversing a list that contains a none will return a none, versus like, let's say, filtering out all the nuns? Yes, they do, in the sense that like the traverse laws provide an axiom, right? Like the traverse laws ensure that let's go to traverse. The traverse laws ensure that this traverse operation meets certain characteristics. And if they meet those characteristics, then we've got a set of axioms about the behavior of our system. And then we can do things like prove what various results will be for different types that meet their same axioms. So like if you take a traverse of list using like the kind of normal implementation of traverse, or the obvious implementation of traverse when you try to implement it, and you took a like an option, stuck it in for G, again with now the normal sort of obvious applicative implementation for option, the one that we actually derived as a group, a few weeks ago, and you work through all the math, all the substitution, given the axioms that the laws give you, you'll see that like that's the only way they could be implemented with those two definitions. Now remember, there were different instances for different type classes, right? I think we talked about two different possible applicative definitions for option. And so if you have alternate definitions, you might be able to change the behavior. But in short, like if you really just have like a list of options, and you want to get just the sums out, the traversable type class is not going to help you. There is a way to do this. In this case, it's this method called unite. At least with option, like the idea here is that it's going to filter out all the nones and just remove the sums, like remove the wrapper of the sums. So you're not getting an optional list of int, you're just getting a list of int. And unite comes from a completely different type class that we'll talk about at a different point. But it does not build off traversable, it actually builds off monad. And there are other ways to swap type constructors, like to go from an f of g to a g of f. Like traverse is not the only type class that does such a thing. There are other type classes that do it. I don't think we're going to talk about any of the others, at least in the current agenda. But there are some other ways to do it. And I want to say like Scala Z actually defines two. So Scala Z defines traverse. The dual of traverse is this type class in Scala Z called distributive. You can see it also extends functor. And if you look at the only abstract operation, you can see it's sort of the same as what we were working with, but some G's and F's have been moved around. So remember, traverse sort of looked like this. I'll put it all in. Oops. All right, so traverse is defined here, remember, as being an f of a and an a to g of b gives us a g of f of b, and we require an applicative for g. Distribute, instead, you start with a g of a. Even though we're on a type class for f, we're going to start with a g of a. We're going to have a function from a to f of b. So we've swapped the position here of f and g, and then we end up with swapped f and g's on the output. One advantage of this particular encoding you can see is that while we have a stronger or a different requirement on f, we require that f be distributive, we have a much weaker requirement on g. G is only required to be a functor. So again, it's just a different way of doing things like what traverse accomplishes, and you may need this in some cases. But by far, traverse is what you'll use almost in every case that you run across in normal Scala day-to-day stuff. Any other questions? All right, then I think that's all for today. Thanks for coming.